Hi, this is Angela Galloway. I'm working on Math 146, and we are in Chapter 12. This is still Section 1, but this is going to be the second part of Section 1. And so Chapter 12 is our Unit 4 assignments. So what we're looking at now is how to organize our data. Okay, so last time we talked about collecting the data. We looked at the difference in sample and population. And we also looked at the different types of data we could be collecting. We could be collecting quantitative data. Quantitative data is data that are numbers, okay? So like if you're collecting people's age or doing something with time or weight or height, any of those things are going to be numbers, right? So that is going to be quantitative data. Qualitative data, which is also called categorical data, is usually going to be words. So like when you're looking at somebody's gender or their race or their political affiliations, all those things would be considered qualitative data. And that's what we're going to talk about first today. We're looking at organizing qualitative data. So once you get your data, you are going to know if it's qualitative or quantitative, okay? You're going to look at, do I have numbers here or do I have categories or groups or words, right? So if you've got those groups that you're putting people into, we've got this qualitative data, okay? The way we can organize qualitative data, and really the way we can organize quantitative data too, we can do this, but we're just starting it with qualitative, is by using a frequency distribution. All a frequency distribution does is it lists each category of data and the number of occurrences for each category of the data. So frequency is really just a fancy word for count. Okay, we're just counting how many people fell into each group. So let's say we did a sample of 40 Kentuckians and we asked them what their highest degree obtained was. So when we went out and asked them, we would have a list of 40 different answers. One person said high school, one said master's, one said bachelor, somebody else said high school, somebody said doctorate. So we have this big list of all those types of degrees. Then what we would do is compile that list and put it into this frequency chart. So what it tells us is the type of degree that the person had or could have chosen, and then the frequency. So how many people fell in that group? So for high school, we had 5. For associates, we had 6. For bachelors, we had 15. Okay, so this just tells us how our data, it's basically a summary of the data. Okay, so that's a frequency chart. Now what is the next step of a frequency chart is called a relative frequency distribution, okay? And so the relative frequency looks at the frequency relative to the entire sample size, okay? So the difference here would be in a frequency chart, I could say 5 people from my sample said they had a high school degree. All right. But if I convert it to a relative frequency chart, I can say 12.5% of my samples said they had a high school degree. And often those percentages make a little more sense to us than just hearing a count, right? If I know 12%, I immediately can think of, about how big that group is or how that might be interpreted for the entire population, okay? So how do we find this relative frequency? It's pretty simple. You take your frequency, which is the count or how many people fell into the group, and you divide by the sum of all the frequencies or by your total sample size for the group that you were surveying. Okay, so in our case, we had 40 total people. So we go over here for high school, we take 5 and divide by 40. So 5 over 40, could be our answer, or we could simplify that to 1 over 8. Or we can actually divide it in our calculator. 5 divided by 40 is 0.125. That would be the proportion or the decimal. Or if we wanted that as a percentage, we could take that decimal and multiply by 100. So 0.125 times 100. That's how we get things to percentages. And I think we're used to that from our interest section, when we were doing simple interest and compound interest and all that, we did a lot of taking decimals and making them percentages or vice versa. So this would become 12.5%, right? So any of those are okay to use on the relative frequency chart. Okay, you could use the fraction, you can use the decimal, or you can use the percentage. On your homework, just kind of double check how they want you to enter the relative frequency. They may want it as a percentage, they may want it as a fraction. Okay, so just kind of look for that. Now, if they do want the answer as a fraction, make sure you simplify it, right? So like 5 over 40 is actually 1 over 8, right? Because I can divide the top and the bottom by 5. Now in your calculator, if you want to, let me pull that up real quick. I've got it down here somewhere. Okay, so let's say I want to check if a fraction is simplified. If I do 5 divided by 40, I get this, which is the decimal. Okay, if I want to get the simplified fraction, I go to Math and Fraction, push Enter, and this says it's going to take my answer that I just had and convert it to a fraction, and it's always going to make it the simplified fraction, okay? And there you go. It'd be 1 over 8. So that's the easy way. If you're not sure, like if something is simplified, you could put it in there, and if it comes back as exactly what you put in, then you know that it's simplified, okay? So that's just a quick tip there if you need that. Okay, so some other ways we can graphically represent our qualitative data. The first one is a bar graph. We're probably all pretty familiar with seeing bar graphs, right? A bar graph on the x-axis is going to have your qualitative data. So that's going to be what you actually collected, you know, what you were going out and asking people about. So in this case, it was what degree had they obtained. Okay, so we have high schools, associates, bachelors, etc. On the y-axis, we're going to have numbers, okay? So the numbers here that we're going to have are going to be our frequency, or they're going to be our relative frequency, which could be percentages or fractions or whatever we want up there. So you either graph the frequency or the relative frequency. It doesn't really matter. I mean, the graph is going to look the same. The only thing that will change is what the numbers are that you have over there. Now notice that in a bar graph, the bars do not touch, okay? There are spaces between all the bars. So that is how you can look at a graph and know if it's a bar graph or a histogram, which we're going to talk about in a few slides, because a bar graph does have spaces between the bars, okay? So remember that for later. The next thing we could use is a pie chart. A pie chart, you see we've got each of the categories take up one piece of the pie. We figure out what size the slice is going to be by the fact that there's 360 degrees in a circle. So if you want to know how big this angle right here needs to be, you would take 360 degrees and you'd multiply it by whatever relative frequency this bachelor's degree had, and that would give you the size of the circle, or the size of that piece of the pie there. So you use this when you have categorical data, but you can't use it for every time you have categorical data. You can only use it when all your categories add up to 100%. So this one works because if we go back to the previous slide, you can see when we add all the relative frequencies, we get a 1. A 1 or 100% is the same thing, right? 1 times 100 is 100%. So as long as it adds up to 1 or adds up to 100%, you can use a pie chart. Now you might be wondering, well, when would it not add up to 100%, right? Well, it's not going to add up to 100% if somebody didn't fall in a certain category, or if someone fell in more than one category. For example, what if I was collecting data and I asked people, what classes are you taking this semester? And I gave them these options, math, English, history, and art, okay? And I told them to tell me, you know, which ones are they taking? Well, you know, at least most of my students probably are taking all 4 of those, or maybe 3 of the 4, or 2 of the 4. So what's going to happen is I may have only surveyed 30 people, but I may end up with 70 or 80 answers when I get all my data back. So I'm going to end up with something that adds up to more than 100%. And in that case, you just can't create a circle of that, okay? Because the circle would have more degrees than what it's supposed to have. So it's incorrect to use a pie chart for that. but you could use a bar graph, okay? So as long as you have the 100%, you can use a pie chart. Anything else that you can't, then you would just kind of stick with the bar graph. Okay, so moving on to quantitative data. With quantitative data, the graph we usually use is a histogram. A histogram is going to look similar to a bar graph, but the bars of a histogram actually touch. It's going to look like this, where the bars all touch together, okay? And usually the data we see is going to be quantitative. That's what we work a little more with because usually we're collecting data that is numbers. But in this example here, what I did, I was looking for the number of TVs my students had in their house. Okay, so I actually asked my class, you know, how many TVs do you have in your home? And so this was the data that I got back. Unfortunately, I didn't have a lot of people in class that day, but I had 13 total there. And then that's my frequency. The relative frequency there I computed by taking each of the frequencies and dividing by that total sample size. Okay, so 1 over 13, 4 over 13, etc. And you see when we add all these up, we get about 1, and so that would show me that everybody fell into one of these groups. Okay, so then when I'm drawing a histogram, on the x-axis, I have my quantitative data that I asked people about, okay, the data I was actually collecting. So in this case, it was the number of TVs. On the y-axis, again, I have frequency or relative frequency, okay? So to draw the histogram, you just draw the bars up to the height they need to be based on what our histogram or our frequency table says here, and then that would give us a pretty quick histogram there, okay? But histograms, unfortunately, aren't always quick to create, okay? In this case, okay, notice that we only had these options, right, 0 through 6. So there weren't that many options or categories for people to fall into. But in this example here, I'm looking at days to maturity of short-term investments. We had values that went from 36 all the way up to 100. Now, in that case, that would give us like 70 categories, right, that we would have down here if we labeled every single number. And in that case, what we would get is, you know, a histogram that really didn't tell us very much. It's going to be a bunch of little bars that probably most of them go up to 1 or 2 or whatever. And so we're going to get something that just looks like this. It doesn't really tell us anything because everything's about equal height, okay? What we want the histogram to be able to tell us is where does most of our data fall? You know, what is an unusual result? You know, what part of the graph shows very little frequency or very little relative frequency? Because that's going to help us to determine you know, depending on what we're studying, what kind of data we're collecting, that's going to help us determine what is a normal result, what is an unusual result, and that's kind of what we're usually looking for in statistics. So like, for example, if I was looking at the test grades on the last test and I wanted to see how everybody did, if I didn't group them all, if I didn't group them together and I just did the scores, okay, uh, I'd have the options of 0 through 100, basically, depending on what people made. And then probably everybody made a different score. So I'd have all these little bars there, and it wouldn't really give me much information. However, if I group them into tens, so now I'm going to group from a score of 0 to 9, 10 to 19, 20 to 29, you know, all the way up to um, 90 to 99. Okay, so now I'm grouping my scores together. Then I can see, well, where did most people score? You know, did most of them score in the 70s or 80s, or did they score in the 60s or 50s? You know, like, so I can see how people did on the test, right? So I'm probably going to group some of those grades together. And that's what we're looking at here. If you've got a lot of categories, you probably are going to have to group your data in some way. So this is the better of the two graphs, okay? This graph, what I did was I did group them in categories, but I grouped them in groups of about 5, right? So they weren't real big, and I had a lot of data here, and what I ended up with was a lot of categories and not much information about the data. I could tell that this is the highest bar from 66 to 70, but other than that, it looks like everything kind of just falls between here and there. It doesn't look like anything's much more likely to happen than anything else, okay? Now this is the same data. All I've done is change the groups, okay? So notice the groups down here are, well, I didn't mean for that to happen, sorry. Let me undo that. And let me get my highlighter there. That'll make a little more sense. Okay, so these groups now were in groups of 15, okay, instead of groups of 5. So what that made was less number of groups, so more items could fall into each category. And now what I got was something that I can explain a little better. Now what I see here is most of these short-term investments matured in 61 to 75 days, right? It was very rare to get one in 91 to 105 days or 45 days or less, right? So that's kind of what we can tell from this graph that we couldn't really tell from this, okay? So how do I figure out what size to make my groups? These are kind of the guidelines for how to go about that. Honestly, it's one of those things that the more you work with a histogram, the better you get at deciding which category is best to use. So, you know, like when we're talking a lot about this because in your stats project, you will have to create a histogram. So, you know, you can just play with it. You know, you can use these guidelines or you can try, you know, try groups of 5, then try groups of 10, try groups of 2 or whatever, and see which one gives you the best looking graph. And that's not really manipulating the data. That's just creating the best graph you can to interpret what the data is telling you. Okay. So what we can use though, if you don't want to just you know, guess what size you should use for your data, we can go by these step by step. So make sure each data item will fit into one and only one class. Okay, what that means is that if one data, you don't want it to go from 10 to 20 and 20 to 30, right? Because then where would 20 go? Would it go in 10 to 20 or 20 to 30? So just make sure you do like 10 to 19, 20 to 29, etc., something like that. Try to make all classes the same width. I think of course you would do that. Otherwise it wouldn't really make sense. You know, if you have one group that's only 5 numbers and another group that's 20 numbers, it's that would be skewed. You know, that would be showing not an accurate representation of the data. Make sure the classes do not overlap, which really is pretty much the same thing as number 1. And then their guideline is use from 5 to 12 classes. Okay, so usually if you have less than 5, that's not going to be enough. And what you'll end up with is, you know, just like 2 big bars or something like that that doesn't really tell you much about your data. Okay, if you use too many categories, so more than 12 is what they'd say, then you're going to get something like this where it's kind of just a flat line. You can't tell much about the data because you have too many categories. So the way to get your class width using this here is we're saying that 5 is the smallest we want to have and 12 is the most we want to have. So we're going to figure out what are the class widths. So how big would my categories have to be if I only had 5 categories and then if I had 12. Okay, so my data goes from 36 to 100. Okay, so I take 100 minus 36 and that gives me 64. So that's the difference in my range. Okay, it goes from 36 to 100, which is 64. I'm going to take that and divide by 5. And that gives me classes of 12.8. So that's saying if I made each of my classes 12.8, okay, so I started at 36, add 12.8, and then that would be my next cutoff. Then add 12.8 again, that would be my next cutoff, okay? Then I would only have 5 classes. If I divide by 12, I get 5.3. So if I take 36 and I add 5.3 and then add 5.3, add 5.3, you know, keep doing that, those are going to give me 12 classes, okay? So then once I have that, I typically am going to pick something in the middle there. So a width between 5.3 and 12.8. I usually try to go with something that is sorry, I just lost my train of thought. I usually try to go something like that's a multiple of 5. Like I like to use 5, 10, 15, 20, because that's usually the easiest for us to do. But you could use 12, or I mean, you could even use something like 5.5. It's just, we don't really like to work with decimals that much and have to, calculate all those out. So I usually will go with a 5 or a 10 or 15, something like that. So like 10 would fall in between here, right? So I could start with 36 and then go up to 36 to 45, then 46 to 55, etc. And that would give me my width of 10, right? And so that's how you can do it for your data. Now, when we do our histogram for your project, you're going to be using Excel. Okay, and so I do have this handout that I think I have linked on Blackboard. If not, I'll make sure I do when I finish this tutorial here, but this goes through how to put in your data into Excel. Okay, so this is showing a sample data set here. And so the first thing you do is you type your data in Excel. Then you figure out how many classes you will have and what the upper class limits will be. Okay, so this is what we just talked about, how we would do it. And so you see we go through here kind of step by step of how to do that, adjust it, and make it look all nice like that. So that would be the end result. I'll do another tutorial video on how to do the histogram because that'll probably take me an additional 15 minutes. So I won't add that on to this video, but there is those step-by-step guides for how to do that, and you will need that when you come to our stats project. I have not posted that yet. If you're listening to this right after I do this lesson, I haven't posted it yet, but hopefully I'll post that either the first or second week of November so you can have more than enough time to work on it, okay? Okay, the next thing we talk about is stem and leaf diagrams or stem and leaf plots. These basically are just quick ways to create a small histogram, okay? So if you have your data and you just want to know really quickly, what does it look like? Where does most of my data fall, etc., then you can use a stem and leaf plot. Now, typically we only use the stem and leaf plot for small data sets. Okay, and you're going to understand why once you see how we construct these. You're going to realize why you would not want to do this for large data sets. But this is supposed to be something that you would do by hand when you're just quickly trying to see what does my data look like. Okay, so the example here that we're doing is daily high temperatures for a Bowling Green. These were from February 2015. And so this is my data here. This was actually by day. So this was like February 1st, February 2nd, 3rd, 4th. The first thing I did is order from smallest to largest, and that's just going to make your life easier when you're doing this stem and leaf plot, okay? So order from smallest to largest. So you see we go from 15 to 65. Okay, so let's talk about how we're going to do the stem and the leaf. Let me fix this here because it looks like it moved over. Okay, there we go. So the stem and the leaf. The digits to the left form the stem and the rightmost digit forms a leaf, okay? So the digit on the right is the leaf. The rest of it is the stem. So let's say I have these numbers here. Okay, I've got these three numbers. Now these hopefully would not be from the same data set, okay? But we're just using these for example, okay? The last digit is the leaf, okay? So for this one, the last digit is 7, okay? So that's my leaf. The rest of the number is the stem, okay? So the 1458 is the stem, the 7 is the leaf. If I have 65, 5 is the leaf, and 6 is the stem. So just one stem and one leaf in that example. If I have 129, 9 is the leaf and 12 is the stem. Okay, now hopefully when you're working with your data is all going to be close to each other. Like if I'm doing test grades, they're all going to be in the 50s, 60s, 70s, 80s, 90s, etc., right? When I'm doing these temperatures, these are going from 15 to 65. If I was doing maybe salaries, at a company, they may go from 30 to 60,000, but they're all going to be numbers that are similar to each other, okay? So, you probably want to have a data set that had the 65 and this. That would make it very difficult to do this stem and leaf plot. But that's just an example of how we figure out the stem and the leaf. So how is that going to help us create a distribution of the data? Well, what we're going to do is we're going to draw this little cross looking thing. We're going to have the stem on the left and the leaves on the right, okay? So looking at our data, we start with 15 and go up to 65. So what is the first stem that I need? Well, this would be my smallest number. So the smallest stem I need is a 1, right? The largest stem I need is a 6. So I need to number from 1 to 6. Okay, so 1, 2, 3, 4, 5, and 6. So those are all the stems I need for my data. Now what I do is I put all the leaves next to their corresponding stem, okay? So for the 10s here, I only have 1, right? So 1 and 5, so 5 is my leaf. For the 20s, all of these are 20s, right? So I'm going to put all of these in the leaves. So I'll have 2 and a 3, a 4, a 6, another 6, a 7, and a 9. So when I look at just this 6 here, that corresponds to a day that was 26 degrees. Okay, or this tells me that there were 1, 2, 3, 4, 5, 6, 6 days that had highs in the 20s. Okay, so that's how we read it. For the 30s, I have a 3, 0, 2, 4, 5, 7, 7, and 9, and 9. Okay, so notice that if you have numbers that are repeated, you do put all those repeated numbers in there. Okay, I know sometimes they're, when we're listing different things in math, sometimes we don't list multiples of things, but on this one we do. Okay, so we want to list the multiples because I want to know that there were 2 days that were 26 degrees. Okay, I don't want to just say, well, 26 occurred twice, so I'm just going to write it down once. Well, no, we want to represent how many days had those temperatures. Okay, so we want to list all those repeated numbers. Okay, so once we get all these there, if you were to draw bars around your numbers, okay, they don't have to have the bars here. The bars I'm just doing to show my students what we're seeing from this chart. Once I do the red bars around it, you can see that it looks like a histogram just laying on its side, right? It looks like if I could flip this over, that I would get a histogram. And that's great because I don't have to use my calculator or Excel or anything special. I can just write out my data in the stem and leaf plot, and then I can see where my data falls. Okay, and so this tells me that most of our days in February had high temperatures in the 30s, or the most common temperature was in the 30s. Then most of our days had temperatures between 20 in the 20s and the 40s, right? From the 20s to the 40s. And then it was very rare to have a temperature that was in the teens or up here in the 60s, right? So that's just kind of a quick view of our temperatures in February, right? So that's what this stem and leaf plot can tell us. But as you can see, since we have to write out every single data point, if I had 1,000 data points, if I had data for 1,000 people or whatever, or for the entire year in Bowling Green, I'm not going to want to write all those numbers down, right? So in that case, if you have a lot of data, it's going to make more sense to put it into Excel and create your histogram that way, okay? All right, moving on to another graph, a line graph, okay? Line graphs, you're probably pretty familiar with. We see line graphs pretty much everywhere when we look at, a change in time is typically what a line graph is telling us, how things have changed over time. So how prices are changing over time, how satisfaction is changing over time, how sales are changing over time, etc. So this graph up here that I've got, this is from March. It says U.S. consumer spending is up slightly in February, okay? So what would we look for here? What do we look for in a line graph? The first thing we look for is, can we find an overall trend? So an overall trend tells us if the data overall is going up or trending down, okay? So like in this one, we kind of see two trends, right? If we look here, from 2008 to about 2010, we saw a decreasing trend, right? But if we look at 2010 on, we see a slight increasing trend. Why, right? That doesn't mean every single point is increasing, but it means overall we see that the trend is on an increasing trend. And it looks like right now it could possibly maybe be starting where it's just like kind of a flat, trend. It's not really increasing or decreasing. It's gotten pretty flat. Okay, some other things we look for is seasonality. So what would seasonality refer to? Well, seasonality, like it sounds, refers to the fact that sales or shipments or inventory or whatever we're talking about often has a pattern that relates to the season it's in. Okay, so for example, when we're talking about consumer spending, notice that from year to year we see these spikes kind of occur in the same place. Where do these spikes seem to always occur? Well, we're at the end of the year, so why would there be spikes in consumer spending at the end of every year? Christmas, right? If we think about Christmas spending, usually people do spend more around Christmas time. So we see that reflected every year that we have a spike there. We also tend to see a spike somewhere in the middle in the summer, which I would probably say is either one of two things or maybe a combination of both. One could be spending on like vacations and amusement parks, that kind of stuff that people do in the summer. The second would be back to school shopping. When people are sending their kids back to school, they kind of have no choice but to go out and spend a little more, especially people going back to college. They have to buy computers or whatever, buy stuff for their dorm. So we might see that increase over the summer months due to either vacationing or because of back to school shopping, and it might just be a combination of both. Okay, so that would be our seasonality. Now, this is another example here that we've got. This is a graph of gun sales, and the title of the graph was, uh, talking about the gun sales soar after Obama calls for new restrictions. This was updated at the beginning of this year. So what we were noticing in our class is this has a very strong seasonality. Can you see that every single year almost looks like it's just copy and pasted from the year before? Now, the peaks may be higher, but the peaks occur in the same spot every year, okay? So where did these peaks occur every year? It says that the peaks are in December, which I'm guessing, my students said it could possibly be hunting, it could be Christmas shopping, whatever. Okay, so end of the year they see a spike. And then also, it looks like in the beginning, like February, March kind of time frame, which they also said could possibly be a hunting spike there, getting ready for spring hunting season. And they see lows in June and July, which we said could be due to the fact that there isn't a lot of hunting going on in the summer. So, we may see those lows where it kind of lulls out in June and July. Okay, but we see those happening every year. So the next thing we look for is, are there any outliers or unusual points? And in this graph, there's some very strong unusual circumstances. And what we did is we tried to explain, why did those events happen? Why did we see a spike here? The reason why we want to explain them is because we want to know, is this a spike that was unusual, or is this a spike that maybe we're going to see happen again next year? Okay, all these spikes we would assume are going to happen the next year because they happen every single year, okay? But when we're looking at this, notice how here, instead of just one spike, we kind of had two spikes back to back, okay? This was towards the end of 2011. So we said, well, what happened in the fall of 2011? Well, at this dot here, that would be when September 11th happened. And so right after September 11th, apparently there was an increase in gun sales, okay, which we could kind of understand why that might have happened. But do we expect that to happen again the next year? Well, hopefully not. We don't expect to see that spike again the next September. But if we can, oh, I'm sorry. I hope that wasn't too loud. If we can explain that spike, then we can say, okay, we know why this happened and we're not planning on that happening for the next year. Okay. The next spike we see is up here. Now, this is the spike we expect to see right there in December, but we had another one right before that. And so that was actually when Obama was elected. That was the first time. That was the end of 2008. So we're talking about November 2008. Now, during the campaign, Obama did talk a lot about gun restrictions and gun laws. So once he was elected, before he went into office, there was a spike in gun sales because people were, kind of afraid that what if these laws do go into effect, making it more difficult for me to get guns or whatever. And so I'm going to go out and buy some now. Now, since he was elected, we see this increasing trend over time. So our spikes are still occurring in the same spot, but they're getting higher every time. Okay, right? And I think that's something that's probably going to continue to happen if we see Clinton elected in the next few weeks. I think that will probably happen as well. If Trump is elected, we may not see the trend increasing as much because we know he is probably going to be less likely to pass more gun restriction laws. However, if he makes it maybe easier for people to obtain guns, then we might see a spike because more people are able to buy guns. We'll just have to wait and see on that one. So we see this increasing trend over time. All right, this next huge jump here, this was when Obama was reelected. And at the same, well, Obama, I think, was reelected. Let's see. Yeah, he was reelected right here. And then right after that, Sandy Hook happened, the school shooting. And so usually when there is some sort of large shooting or whatever, we do see a spike in gun sales. This also would have been around the same time as I was, well, maybe not. I was thinking there was something else that went on at this time, but I think this was all we identified for this one here. So this kind of combined with the December sales, the re-election, and Sandy Hook all kind of just made this one massive spike for gun sales. Okay. The last one where we see this large spike here, this is also, Christmas sales or the end of the year sales. But around the same time, we had San Bernardino, the shooting there. We also had, there were Paris attacks, Germany, Australia. There were lots of attacks happening in the world at the end of 2015. So we did see a spike in sales there. And so that's kind of what we'd be looking for. These would be considered outliers or unusual points that we don't expect to happen again. And if we see those in our graph, we'd like to try to explain them and say, why did that happen? And is this something that's going to occur on a regular basis? Okay, so how do we create good graphs? These are common mistakes in graph. Improper scaling. One of the most popular ones we'll see with that is not starting your graph at 0, and we'll show an example of that. Unnecessary pictograms. A pictogram is when you're doing like a bar graph, and instead of using the bars, you use like a picture of something like kittens or baby bottles or whatever. You use, the actual picture in your graph instead of using just bars. And usually that makes it difficult to read the graph. Using the incorrect graph for your data, using a pie chart when you don't have 100% of data, using a histogram when you should use a bar graph, that kind of stuff. Too much clutter, okay? Just having too many pictures and colors and 3D effects and all that stuff in your graph. So what are we trying to do a graph for? Why do we do a graph? We make a graph of our data so that anyone can pick up that graph, read it, and understand what our data says, okay? If I have a big sheet of just a lot of numbers, okay, somebody can't pick that up and immediately look at it and know, oh, most people said this answer or most people fell in this category, right? So I put it into a chart or into a graph to help people to quickly look at it and understand what's going on with the data. When I do one of these four things, that hinders people from being able to accurately understand the data, okay? I want my data to be accurately represented by the graph. What that translates to is a boring graph. Okay, I'm sorry, but most mathematicians and statisticians, we like the boring graphs. Okay, we like the graphs that are just bars or just lines, not too many fancy colors or fancy shapes, anything like that, okay? So even though in PowerPoint and in Excel, you can make these really cool looking graphs that are three-dimensional and multicolored and all this stuff, honestly, when you're just trying to interpret the data, interpret the graph, you want it as simple as possible, okay? So tips for creating a good graph, just do the opposite of all these common mistakes, okay? So let's look at some bad graphs. Now, these are all real graphs that were either published or were posted on the internet or whatever. They are graphs that were used somewhere. Okay, now this one right here, just glancing at that, we're looking at different death tolls. Okay, so just looking at it quickly, which one looks like it had the highest death toll? Well, obviously this one here, right? The Vietnam War says 58,209. That is the highest bar, and so we would assume that would be the highest number of deaths. However, let's look a little closer at this graph. Okay, so what is this blue block telling us? If you notice, it says each star represents 4,000 people. Actually, it says 4,000 plus, which is bad too, but so it's about 4,000 people. This is showing the deaths in the earthquake in Haiti, which was 200,000 plus. Okay? So this is actually 3 or 4 times bigger than that. But can we tell that by just quickly glancing at this graph? Well, no. To be able to tell that, I have to read every little number, figure out what it means, and then interpret it. So if I have to do all that work, then this graph really didn't show what it was supposed to. Okay? How could we make this graph better? Well, we just do a simple bar graph. Okay? Now this is going to look terrible. But what this bar graph would look like, we'd have our different things. We'd have, Vietnam War being high. The Haiti earthquake would go past this screen. Okay, it's so much bigger than this. It would at least be 3 of these stacked on top of each other. Okay, so that would give us a very quick idea of how much more catastrophic that earthquake was in Haiti than anything we have seen in the U.S. And I think that was the point of the graph, was to tell us, what a big deal that earthquake in Haiti was. Because, we think of things like Pearl Harbor, 9/11, the Iraq War, Vietnam War, all these things. But even all these combined does not even come close to the number of people that died in the earthquake in Haiti. So kind of a neat looking graph. This would be considered a pictogram because they're using basically the flag to represent the bars, but just not really good at explaining what the data says. Okay, so what about this one here? This is a pie chart, right? What's wrong with this pie chart? It adds up to way more than 100%, right? You can see just adding these, you're almost at 100. Now you've got another 40, another 20, all these 20s here, that's another 100. Here's another 100. So it's obviously not 100. So what's going on in this graph? Let's see where this came from. So this I got from a website that was looking at some bad graphs here. Let me go. This was in the Sun. This is about some elections overseas when they were electing. I think last year they were doing, I guess Britain's general election. I'm not really sure who they were voting for, but it says right here that to get this, we asked voters for their top 4 election priorities. So that means that every respondent gave 4 issues, right? So that's going to add up to probably about 400% here, right? Because not only are people responding with one answer, they're responding with four. So if you ask 100 people, you're going to get 400 responses, right? So this obviously is not going to add up to 100%. So what ends up happening is you have a lot of clutter here, and this really doesn't tell us much information. I mean, you can see that these are the most common concerns, but you could have seen that with a bar graph and it would have made more sense because it would have actually not added to 100. Makes more sense to just do a bar graph there. So this problem would be that you should have chosen the correct graph. They had the wrong graph for that one. This one now is a very simple version of a pictogram, okay? So instead of using bars here, they used candy corn, okay? So this is looking at Halloween candy collected. They looked at the number of pieces of candy and these two people, okay? So Shayna collected about 17 or 18, I guess, and Michael collected about 36. So Michael collected about double of Shayna. But looking at this candy corn, does it look twice the size of this? Well, not really. It looks much bigger than twice the size. But the reason why that is because our eye looks at the entire shape there, right? Now the height, if we had just done a bar, okay, pretend like this is straight. That's a terrible bar, I'm sorry. But pretend like we've got these bars here, okay, and we're just comparing them. Now we could easily see the height of this and the height of that. So we would say, well, he collected about double what she did. But when we look at this candy corn, it looks so much bigger. It seems like, wow, he must have collected like 3 or 4 times what she collected, right? But that's because when we increase this, when we double the size of this candy corn, it not only gets taller, it gets wider. And so now to our eye, this just looks much bigger than what this is, okay? And so it looks like it's representing a lot more than what it actually is, okay? When we're looking at bars, they're all the same width, so really the only thing we notice is the difference in the height, and that's okay, and that's going to tell us the difference in those categories, okay? So the problem with this one would be that they used a pictogram instead of just a basic bar graph. Okay, now looking at the problem with the axis. This was talking about federal spending as a share of the economy, okay? And what they were trying to show, and this was a few years ago, but what they were trying to show was how much more the federal spending was going to be under the the Democrat budget blueprint of 2009 for 2020, okay? That was the blueprint they were suggesting was going to go forward, okay? And so looking at this graph, yes, it does look like this blueprint would increase federal spending 2 or 3 times, right, compared to what happened during the Clinton presidency and during the Bush presidency. However, notice that this starts at 17, okay? So the difference here actually is just a few percent. If we redo this graph and start at 0 like you should, now you see that yes, the Democrat budget is higher than those in the past, but it's not 2 or 3 times bigger, okay, right? It's just a few percentage points bigger. So that, something like this could be used to make people think that it's a bigger increase than what it really is. Once you see it here, you can say, well, yeah, there's an increase there, from here to there, but it's not 2 or 3 times bigger like it looks like here. So that's what we were talking about, not starting your axis at 0. Now this last one here, we have which company saw a greater increase in sales? So this one or this one? Well, your eye immediately would look at it and say, oh, this one had a bigger increase because look how sharp this increase is. This one's more of a flat increase, right? But if you look at it, it's actually the exact same data. The only thing we've done is we've squished this one together a little more. This one we've pulled out a little more, okay? So what you can do is by manipulating those axes, you can kind of change what the trend looks like. Now, you can't necessarily make it look like an increasing trend instead of a decreasing, but you can make it look like a sharper increase or a less sharp increase, more of a gradual increase. So that's something that people will sometimes try to do when they're trying to show like maybe their sales are better than they really are, or that incomes are going up quicker than they really are. They can adjust kind of that width of the graph, and that can make a difference on what our eye sees. So you always kind of want to check and just see, what does that really look like? Is that really that big of an increase from January of 13 till November of 14 to go up that much or whatever? You can kind of think about that so that your eye is not deceiving what you're actually seeing there. Okay, so that's the end of 12.1. We'll have another video to help you through how to create a histogram. So look for that. That one you'll be using once you get your stats project. And then I'll also have videos for the rest of the sections that we will be covering in Unit 4. So until next time, thanks.